Hello everyone, welcome back to another lecture of spatial statistics and spatial econometrics. This is the 15th lecture of this series for spatial statistics and spatial econometrics. And today we will be moving forward from the variogram, theoretical variogram, an experimental variogram, and a variogram model, where we really had this, we got to a point where we have a generic device to which if I provide a spatial lag measure or spatial distance between any 2 points, that is h, it provides me a measure of spatial contiguity between those 2 points, right? So today we are going to move one step forward and look at an example, start with an example where our basic aim is to predict unknown values in space, right? So we have been building up to this point to be able to really predict. One of the objectives is to predict unknown, or unsampled locations in space. And then from there, we will go on to the, next module, which is spatial regression, wherein we will take this leap from, correlation to causation as well, right? Okay, so let's move forward. So I have this slide titled as Spatial Dependence Estimation and Prediction for a Non-Stationary Domain. Like I said, we are going to work with an example, but in this example, we are going to, assume that we are starting with a non-stationary domain. So, we are working with a real-world problem. It's not going to be a textbook, representation. It's going to have issues of its own. So, as an analyst, how do we go about tackling these issues systematically, eventually getting to a point where we are using a variogram model to be able to provide a spatial prediction. Okay, so we will start with an example, and then finally towards the after this lecture, after lecture 15, you will have learned also the theory of spatial interpolation, or basically spatial prediction. Okay, so we have to start with a non-stationary domain. I'm going to begin with an example. I'm going to begin with an example for groundwater levels data in one dimension, right? So one dimension means it's really the real number line. So basically we are walking on a real number line, and at different locations we are measuring the groundwater depth. Okay, so let's draw that representation here. So we have a ground surface. On this ground surface, I have locations S1, S2, S3, S4, S5, and S6. Okay, at each location, I have a realization that is Z of S1 equals 2, so 2 meters depth, right? Z of S2 equals 5. Z of S3 equals 12, Z of S4 equals 8, Z of S5 equals 15, and Z of S6 equals 20. Okay. Now, even before we do anything, we start working with these data, it's pretty clear that as I'm moving along the real number line from location 1 till location 6, the depth of groundwater level is on average rising, right? We sort of sense a rise in these values for this particular example, right? And this x-axis, I'm just going to say x-axis is my ground level, right? This is my way of this is where I go in, dig a well, and figure out the value of, depth. And, Z of S1, so Z by itself represents groundwater depth. Okay, just for completeness. So we're going to draw these data on a graph. So we have, let's say, groundwater depth on the y-axis, and on the x-axis, I have my, locations. So I have my S1, I have my S2, S3, S4, S5, S6, and S7. So I don't have a S7, so I'm going to stop at S6. And let's say on the y-axis, I mark levels 5. So this is 5 is basically groundwater depth. So on the y-axis, I have groundwater depth. Let's say it is in meters. And X is also in meters. So as I'm moving from S1 to S2, the distance between them will be given in meters. Okay. Okay. And let's say 5, 10, 15, 20, and 25. Okay. So at S1, I know that at S1, the value of observed value is 2. So it's somewhere around here. At S2, the value is 5. So it is somewhere here. I'm just going to mark them, slightly with, with some approximation, but I'll do my, best of my ability, mark them to scale. Okay. So ZS4, 5, and 6, that is 20. Okay. There we go. Okay. So as I saw, when I looked at the numbers, I felt that as if when I'm moving from S1 through S6, the groundwater depth is sort of rising. So the groundwater situation is becoming worse and worse as we traverse from S1 to S6, right? When I plot this data, I'm actually able to, work out a trend between these values. Okay, so if I were to, try and, plot this, I'm going to have something of this. So this is the spatial trend in groundwater data. And this is not, this figure, although is in space, shouldn't surprise you. Imagine the groundwater data were some kind of a time series. Let's say it was GDP. And S1, S2, S3, S4, S5, S6 were time points. So then, I'm really looking at a time trend. So trend is not something that is very new to us when we, as statisticians or econometricians, right? But to be able to look at a spatial trend and to plot it, that is perhaps, quite new. Okay, so let's see what this trend effect really does. So if I look at these values, I mean, I should be able to also figure out what is, that G bar, that is the mean value of groundwater depth for these data is 2 plus 5 plus 12 plus 8 plus 15 plus 20 divided by 6. I believe if you sum them, it will be 52 by 6, so it will be somewhere around 9 meters. Okay, so this is something we are used to. We are used to starting with some kind of a summary of these data. I've just pointed out that the mean groundwater depth in the domain that I'm studying. So my domain of interest is S1 through S6, right? So my domain of interest D comprises of locations. Well, we can say locations, S1 through S6. Okay, even though S1 through S6 are discrete points, every point between them is a potential for observing groundwater levels. And the locations where we do not get to measure or sample these data, well, those are the locations where we should be able to predict these data. So the aim of this exercise really is to be able to say, take a point between S3 and S4, call it as 0, and we want to, our aim here is to estimate or predict the value of groundwater depth at location S0, right? This is what we were after. This is a prediction exercise. S0 again is a representative unknown or unsampled location. Every other location that remains unsampled is a candidate for prediction, right? So what do we do? Well, as step one, what we will do is we will model spatial dependence in data, using the given sample, right? So when I say data, I basically mean the data that is given to us, the data set that has been given to us. Why do we do that? Well, if we are able to predict spatial dependence, right? Remember, I am looking for a point S0 where there is no observation. I want to know where would S0, the value of groundwater level or depth of groundwater level, what will it be at S0? What has been happening before S0 is that there is a rising trend from 2 till 12. So it's a very quick rise. But as soon as I come to S4, it seems like there is a drop. So this is pretty confusing as a statistician. If they kept rising, I could have said, maybe these values, the value is between, 12 and the next higher value, right? But what happens is that S4, it comes down, GW comes down, and at S5, it again goes up drastically, right? So I don't really know, it's really hard, it's non-trivial to predict what should be groundwater depth at the location S0. Now we want to model spatial dependence so that we'll be able to know what is the strength of dependence around S3 and around S4. If the spatial dependence is very strong around S3 and not so strong around S4, then S0 will be nearer to S3 in terms of its representation of groundwater depth. If it's vice versa, it might be that you have a greater spillover coming from S4 than from S3, right? Clearly, S0 is closer to S3 and slightly farther away from S4, so that will also be accounted for. So there is closeness and there is also this spatial dependence, the strength of spatial dependence at those two locations. That is what is going to be, revealed by the variogram. So we will use a variogram and more specifically a variogram model, right? Apart from that, I would say clearly, the knowledge of this trend, the knowledge of this trend of spatial trend in the x direction, in the positive x direction, will help or helps or aids prediction, right? Help in predicting groundwater level at S0, right? However, this very trend will make our data non-stationary, right? So, however, the trend effect makes our data non-stationary. We will just look in a minute how trend makes our data non-stationary. Now, having this trend effect, this kind of structure in the data, which is coming in as trends, it could be a non-linear trend as well, right? Other than that, you might have regimes, right? It might be that S1 through S3 is data in regime A, and S4 through S6 you have a data set in regime B, right? Whichever way this structure arises, right, to a continuous trend or a piecewise, average or piecewise linear, representation, this structure provides me some knowledge that I can use to then predict the S0 value, right? But on the other hand, this makes my data non-stationary, which means all my definitions of G bar, my definition of variogram, they are all useless. So basically the variogram is not defined because the variogram requires intrinsic non-stationarity to hold for us to be able to write that, second moment property of spatial data. Okay, so there is a pro and there is a con of spatial non-stationarity in data, and this sort of, provides a trade-off due to data structures, structural breaks or patterns in data. Okay, just a remark so that it sort of stays with us. Okay, so with this, now that we have an understanding of this trend, let's go ahead and try to sort of model this trend. Okay, so say we model the spatial trend. And when I say that, what I really mean is that you have groundwater level at location Si. I'm writing that as beta 0 plus beta 1 I. So I is the index for space. When I move from S1 to S2, this movement from 1 to 2 tells me that S2 is located in the positive x direction from S1, and similarly then S3, S4, S5. So as the index I increases, I'm moving along the x-axis. So this is a convenient, specification that the data structure allows me. And then I have a random error. So this is called as a linear trend regression. Again, those of you who have seen time series analysis must have been definitely aware of this. This is a simple linear regression model. So we are introducing a regression model. We are modeling the variation in G of Si, which is a spatial variable. On the left hand side, we have a linear model of what I want to explain, right? So my dependent variable, that is groundwater depth at location Si, which has a systemic, portion of variation. So systemic portion or component of groundwater evolution in space, right? How groundwater levels evolve in space, is given by this systemic portion. This clearly exhibits spatial trend in data, right? The parameters beta 0 and beta 1 are called as model parameters, right? So beta 0 and beta 1 are model parameters. Okay, beta 0 is an intercept, which is really a representation of, global mean, a representation of mean values. Beta 1 is the change, the marginal change on moving to one step from lower x value to a higher x value, right? So it is a step change in groundwater depth upon moving from location I to location I plus 1, right? So the change in GSI between location I and location I plus 1 will be definitely driven by this systemic portion beta 0. UI, on the other hand, is called as the random error. This is the variation in groundwater levels that is not explained by the trend, which is not surprising. You see, the trend, is one way of learning about what's happening with groundwater levels in space. There are so many complex, mechanisms or processes in place that really deliver the groundwater level that we see. Well, there is draft, there is extraction of water at different locations. There is, a recharge in different locations. There are anthropogenic impacts. There is rainfall, whether, rainfall is the same at all locations S1 through S6, or you have some higher level rainfall regions and some lower level. All these factors that can explain groundwater level, which are different from a mean and the trend effect, which we have included in our systemic portion, will all go into the random error, UI. It's called an error because this is the error of our model. The model is beta 0 plus beta 1 I, right? And this error is one where we assume that on expectation, this error will be 0. Okay, so very quickly, if you were to go back to the previous slide where we drew this data, well, this trend line has an intercept and it has a a slope. A slope is the step increase in moving from I to I plus 1. So this is beta 1 representation, right, on your screen. And you see that the predicted value at S6 from this model will be beta 0 plus beta 1 times 6. It will be a value on the yellow line. Now this predicted value, which is in black, and the truth, which was the actual value, observed value, which is in blue, are different, right? This difference represents the error from our model. Okay, this is the error in the regression, linear trend regression on on the previous slide. Okay, so let's move forward. Okay, so now I have my understanding of this model through a spatial regression. Why is it spatial regression? Because it is explicitly exploiting space in order to specify the random variable, that is a groundwater depth, in a given region or domain D. Right? Now straight away you will see that if I were to write the expectation, expectation of G of Si, it will be expectation of beta 0, which is a constant, which is just beta 0. So expectation of a constant is the constant itself, plus beta 1, which is again a constant, and I is deterministic. So location is not random. I is, when I say location is S6, I mean it is exactly S6, not like it is S6 plus minus somewhere. There is no such measurement error or any kind of error in location I. So my expectation at of GSI is just beta 0 plus beta 1 I, because the expectation of UI is 0. Similarly, if I were to go to a separate location as J, here the expectation will be beta 0 plus beta 1 J. This implies that the expectation of G of Si will be not unequal or not equal to expectation of G of Sj for all ij pairs such that I is not equal to j. So that means the expectation, the first moment, that is the mean at different locations, is different due to the trend effect, specifically due to the trend effect, right? This is where the non-stationarity is coming from, right? This is the definition, the first condition of stationarity, be it intrinsic or second order stationarity, is that the mean is the same at all locations. Well, that is not the case here. So that's why trend leads to non-stationarity. So let's move on from the first moment characterization that leads to the reason for non-stationarity to the second moment characterization, that is the variance of G of Si. Now, the purpose of a regression model is to be ultimately be able to explain the variation of the dependent variable. So ultimately, as an analyst, when I'm specifying a regression model, I'm trying to explain the variation in groundwater levels, right? So if I go back, if I look at the raw data, there is this variation in groundwater levels that is happening. Of course, there is a trend effect, right? That's why I include it into my model. But ultimately, I want to be able to do my best in order to explain this variation in groundwater levels, which are going up and down through space, right? Now, so second moment characterization is about, what is the total variation in the data. The total variation in the data will come from the second moment, that is the variance of G of Si. Now, part of this variation will be explained by the trend, right? The trend characterization, that is a systemic portion as we have specified here, but the part that is not explained will go into the residual. So we characterize, or we sort of represent variance of GSI as sigma squared T, which tells me the trend component, plus sigma squared U, right? So the trends are explaining some variation in the data and the rest is remaining unobserved. Okay, so this is just to sort of get an understanding of the regression model. So now say we estimate estimate beta 0 and beta 1 from the given data. Data set using what is called as the ordinary least squares method. Okay, that is the OLS. Now, if you have not heard of OLS, don't worry about it. We are going to move to spatial regression in the next lecture, and we're going to introduce what OLS is and what a regression is. And then we'll adapt it to the space dimension, spatial dimension, and then move from there to the causal inference idea. Okay. So say we estimate beta 0 and beta 1 from the given data set using the ordinary least squares. The idea is that I have this true parameter beta 0 and beta 1, which were really a representation of what I should be expecting. Now I have estimated them. I call them beta 0 hat OLS and beta 1 hat OLS. This beta 0 hat and beta 1 hat OLS is nothing but values that I'm able to reduce from the given data set. Right? Beta 0 hat will be the intercept where it touches the line, right? Touches the y-axis, the regression line, and the slope at which it is rising, that slope is beta 1 hat, right? So it will be an actual numerical value, right? So once we get our beta 0 hat and beta 1 hat, we are able to construct a mean and trend filter for our groundwater data. What does that mean? Well, once I have my beta 0 hat and beta 1 hat, I can put that back into the regression model. That is to say, G of Si minus beta 0 hat minus beta 1 hat I. Remember, this value is nothing but the residual that is remaining than when we remove both the beta 0 and beta 1i effect. So we have the ui left. Because we have now included real actual numbers as beta 0 hat and beta 1 hat, and they've come from the data, well, this value is nothing but u hat I. Right? When I say u hat I, basically it means residual at location I. So I could have actually written this as u hat Si. Or I could then also write this as G star Si, where G star Si is the demeaned and detrended ground water level, variable. What does it mean when I say that I'm removing the mean and I'm removing the trend? Like I said, beta 0 is a representation of the mean value of groundwater level, that is expectation of groundwater level when I is 0, right? And beta 1 is the trend effect, right? Now, the point is that when I estimate these things from the data and deduct these from data, what I'm doing is that I'm first, I am removing the mean groundwater level, and here I'm removing the trend in groundwater levels. Okay. What does that mean? Let's figure it out going back to our graphical representation. So we'll do it on the next slide. So let's say I have my data again. Let's just remind ourselves really quickly that I was working with data at locations S1, S2, S3, S4, S5, and S6. And the groundwater levels at these locations were 2 meters, 5 meters, 12 meters, 8 meters, 15 meters, and 20 meters. So my original plot looked something like as under, okay? Let's plot this. I have my locations S1, S2, S3, S5, and S6. And on the x-axis, I have 5, 10, 15, and 20, and 25. Okay, so I'm going to try and do as good a job as possible to plot this, to create this, construct this plot to scale. Okay. All right. We have S5 is where we hit the groundwater is at 15 meters and S6 where the groundwater is at 20 meters. So this is the true data set, and we had drawn the trend effect here, earlier. Again, trying to sort of keep the representation about the same, if not exactly the same. Okay, so this is my trend effect. This is my original plot. I'm just going to call this my original plot. Okay, now let's sort of draw the detrended and demean plot, right? So now I'm going to draw what I'm going to call as the filtered, filtered groundwater plot. That means when I say filtered, I mean demeaned and detrended groundwater levels. Okay, so let me draw that. Try and be as accurate as possible so that you can actually compare these two plots. S1, S2, S3, S4, S5, and S6. On the x-axis, I have my 5, 10, 15, 20, 25. Now, after I demean my data, where is my data going to be, meaned at, right? So first of all, I have detrended the data. So I have my trend like this. When I detrend it, it becomes flat. And when it becomes flat, at around the value of 9, that is the G bar, that is the average groundwater, depth, that is G bar equals 9, I'm going to have my data, centered at this mean. But what I've also done is that I have demeaned my data. That is to say that my mean value will now slide to 0. Right? So because I've taken out the mean, I've taken out the trend. So first I've taken the trend, I've flattened it, right? And then I've taken it from 9 to 0. So I'm going to try and draw my resulting data set like that. So in order to do that, I'm going to just shift the axis a little bit on the y-axis such that it is convenient for me. What I'm going to do is I'm going to draw 0 slightly upward, just for my convenience. This is just a convenient plot. So I have my mean that has now moved to the point which is 0 on the y-axis. Okay, and if you look at the values that they will be after demeaning and detrending will be something as follows. So it will be somewhere here, slightly above that at S2. At S3, it is a little bit more. S4 drops down, right? This is S4. S5, again, it is slightly below. And then S6 is slightly above. Okay, so now I have my values centered around the mean. So the mean is what is giving me your UI hat. So what, instead of, GSI, which is on the left hand side plot, I am plotting G star SI, which is the demeaned and detrended value. Okay, remember G star SI is GSI minus beta 0 hat minus beta 1 hat I. Okay, now when I plot a variogram, when I estimate a variogram, right, variogram estimation What will it do? It will provide me a spatial dependence structure for this entire data set. Provides a spatial dependence structure or strength at each observed value. What that means is that, when I observe, at S3, when I observe this blue dot, what's going to happen around S3 is that the values will look similar. But as I move away from S3, those values will start to look less and less similar to S3 and more similar to the mean, the global mean, right? Because if I get too far away beyond the range, then I have no predictive value coming from, the observed value at S3. So what happens is that as I move on the right of S3, I have values which are similar to S3. But as I move forward, this spatial dependence goes away and it starts to converge with, the point which is the no correlation point, no spatial correlation, that is beyond the range that is estimated from the variogram, right? So after the range, these values are going to be equal to the mean because there is nothing to learn from the neighborhood. As I move closer to S4, well, there will be again something to learn and these values will start to look similar to S4. Similarly, as I keep moving forward, the data that I have will start to look as shown on your screen, right? This is how the spatially dependent data are going to sort of, we are going to be able to predict a value as 0 away from the sample location in our data. Okay, so if S0 was somewhere here, let's say it was closer to S3 and farther away from S4, then the S0 at S0 location, the cross will give me the d-meaned and d-trended value. Now, in order to actually retrieve the actual value, I will have to add the trend back to these data, right? So I need actual GSI. Right now, I have G star S0, right? So I have G star S0. I want G of S0. So I'm going to go and back and add this component which I had removed from the data. Okay. So as a next step, I'm going to say add trend. So we had detrended. Then because detrended data is stationary, we estimate our variogram, we get our G star SI, and then we add the trend back to the data. Okay, add trend back to data. Okay, so if I do that, I'm going to use a different color. Here I have again S1, S2, S3, S4, S5, and S6. So what I'm doing now is I'm adding the trend back to the data. So I have my trend line here like this. I'm going to have to just, add the trend as well as the mean to the data. So the data will look like the following. So I have my trend added back to the data. Let's say this is the trend added back to the data. Then, I have my representation will sort of change to the following. Okay, so I'm just drawing these things to, not to scale really, but, just to give you an idea of how these things would look like if you were to work with a real world problem like this. Okay, so if you were to conduct this prediction, then you can go between S0 and S3 and S4, let's say to S0, and now you will have your unknown GS0 estimated from these data. Now, let's say we did not conduct this detrending effect. Let's say we did not do that, right? What will happen then? We will work with a d-mean data set. Of course, the data are going to be, centered around this G0 when they are predicted. What's going to happen is that the variogram representation will look like the following. So I'm going to use the green ink for that. Now this green ink is representing the scenario when I did not d-mean and d-trend my data. Okay. So I hope this lecture was, was fun for you, and I look forward to having you in the next module, which is called as spatial econometrics. Thank you.